Just weeks ago, astronomers expected 3I/Atlas, our third ever interstellar visitor, to flicker quietly past Mars. Instead, the impossible happened. In just 48 hours, this object erupted, glowing 6 times brighter than any cometary model predicted, and building a green, carbon dioxide-charged cloud half as wide as the Sun. Now, Earth's telescopes are helpless as Atlas rushes toward Mars at nearly 70 kilometers per second, slipping beyond our view into the solar glare. Why is this supposed alien traveler breaking every rule? Is it revealing new physics or hiding something far stranger? What secret is unfolding near Mars, and can anyone on Earth decode it in time? 3I/Atlas currently sits about 2 astronomical units from the Sun, twice the distance separating Earth from our star, or nearly 300 million kilometers away. At this moment, it's moving inward at a remarkable 58 kilometers per second. That speed is difficult to grasp. It's more than double the velocity of any planet in the solar system. Mercury, the fastest planet, orbits at just under 48 kilometers per second. 3I/Atlas would cross the gap from Earth to the Moon in a little over an hour, a journey that took Apollo astronauts 3 days. As it approaches perihelion at the end of October, its speed will climb even higher, reaching nearly 68 kilometers per second, an extreme that pushes the boundaries for natural objects within the inner solar system. For comparison, the Parker Solar Probe, the fastest human-made object, will eventually reach about 200 kilometers per second, but only after years of gravity assists and careful planning. 3I/Atlas achieves its velocity simply by falling, pulled by the Sun's gravity on a hyperbolic path. On the astronomical magnitude scale, 3I/Atlas has reached magnitude 12. This number, while technical, carries real meaning. The faintest stars visible to the naked eye are around magnitude 6. Each step on this scale represents a significant change. A difference of 5 magnitudes means a 100-fold change in brightness. A jump from magnitude 16 to 12, as seen with 3I/Atlas, is a leap of about 40 times in brightness. Yet even at this level, the comet remains invisible to unaided eyes. Only with a mid-sized telescope and clear, dark skies do amateur astronomers catch a glimpse. For most, it's a ghostly smudge, barely distinguishable from background noise. The comet's brightness is not just a matter of optics, it reflects the sheer amount of sunlight being scattered by its expanding coma. The nucleus of 3I/Atlas is still hidden, shrouded by a thick cloud of gas and dust. Estimates for its size range from a compact 0.3 kilometers to a more substantial 5.6 kilometers across. The coma, the glowing envelope that surrounds the nucleus, has expanded to nearly half the diameter of the Sun itself. This is not simply a visual effect. The coma is a real, physical structure, hundreds of thousands of kilometers wide, made up of ice and dust vaporized by the Sun's heat. It reflects and scatters sunlight on a scale rarely seen at this distance from the Sun, marking 3I/Atlas as an outlier among comets. Trajectory calculations confirm that 3I/Atlas is following a hyperbolic path. It is not bound to the Sun. This is a one-time passage through the solar system, never to return. Its closest approach to Earth will be no nearer than 1.8 astronomical units, so there is no danger of impact or debris. The urgency lies elsewhere, in the fleeting opportunity to observe an interstellar visitor as it races through our solar system, soon to vanish into the Sun's glare. Every metric, distance, speed, brightness, places 3I/Atlas far outside the familiar patterns of solar system objects. The numbers resist easy comparison. With a Mars flyby ahead, these facts set the baseline, anchoring the story in hard, unyielding data. Within hours of the brightness spike, the Comet Observation Database, COBS, lit up with alerts. Amateur astronomers in Australia posted the first flagged measurements, noting a 6-fold increase in light output over just 2 nights. Was this a true outburst, or an artifact of photometric scatter? On October 3rd, 3I/Atlas sweeps past Mars at a distance of about 30 million kilometers. Close in cosmic terms, yet still well outside any risk zone for the red planet or its orbiters. The comet's trajectory is relentlessly outbound, defined by an eccentricity greater than 1. That number, simple as it sounds, means the object is unbound. an interstellar visitor making a single, irreversible pass through the solar system before vanishing into deep space. For Earth, the closest approach has already come and gone, never dipping below 1.8 astronomical units. In practical terms, that's more than 270 million kilometers, nearly twice the distance to the Sun. No debris, no impact threat, no meteor storm. The only thing at stake is the data we can collect while the window is open, but that window is shrinking fast. As 3. I/Atlas barrels inward, the geometry of its path conspires against ground-based astronomers. The angle between the comet and the Sun, known as solar elongation, narrows day by day. By October 21st, this angle dips below 30 degrees, a critical threshold. Below that, even the most advanced telescopes struggle to pick out the comet's faint glow from the overwhelming brightness of the evening sky. For most observers, the practical viewing window closes in early October, just as the comet makes its closest approach to Mars. The timing is unforgiving. Perihelion arrives on October 29th or 30th, when 3I/Atlas will pass within 1.36 to 1.4 astronomical units of the Sun. At that moment, its speed peaks near 68 kilometers per second, and its activity is expected to reach a maximum. Yet from Earth, the comet is lost in solar glare, invisible to even the largest observatories. This blackout period, spanning from early October through early November, means that the most dramatic phase of the comet's evolution will unfold beyond the reach of direct human eyes. All of this is mapped out by orbit modeling, which tracks every nuance of the comet's path using data from hundreds of observations. The numbers are unambiguous. 3. I/Atlas will not return. Its hyperbolic trajectory guarantees that any mysteries left unsolved in the coming weeks will remain unanswered for generations. The urgency is real, but it's not about danger. It's about the rare chance to witness an object from another star system as it interacts with our Sun and planets, before it slips away forever. The only way to extend that window now is to hand off the chase to spacecraft already circling Mars, each armed with their own suite of instruments and their own shot at capturing a piece of this fleeting encounter. The scramble for data began the moment 3I/Atlas broke from its predicted path. Observatory schedulers across the globe found themselves in a race against time and against the Sun. With the comet's light curve veering sharply upward, major facilities activated target of opportunity protocols. The Hubble Space Telescope, already oversubscribed, carved out an emergency imaging slot, capturing ultraviolet and optical frames as the coma ballooned. Each HST exposure had to balance the risk of saturation against the need for detail, with instrument teams recalibrating on the fly to keep pace with the comet's rapid brightening. Not far behind, the James Webb Space Telescope secured a rare, committee-approved window for mid-infrared spectroscopy. On August 6th, JWST's NIR-SPEC instrument locked onto the coma, registering an unusually high carbon dioxide to water ratio, about 7.6, far above the norm for solar system comets. This finding, flagged in real time to the Minor Planet Center and shared in private Slack channels, set off a wave of requests for additional spectral coverage. The Gemini South Observatory, operating out of Chile, was next to pivot, grabbing a sequence of optical and near-infrared snapshots. Gemini's wide field and fast switching allowed teams to monitor subtle changes in coma structure and color, even as the object's brightness fluctuated from night to night. Meanwhile, SphereX, NASA's all-sky infrared surveyor, adjusted its scan cadence to catch brief glimpses of the comet's evolving spectrum. Though SphereX wasn't designed for rapid follow-up, its broad wavelength coverage provided a unique baseline for tracking volatile emissions as the comet crossed different solar distances. Each facility brought its own strengths and its own constraints. HST could resolve fine coma features, but only in narrow time slots. JWST delivered unmatched sensitivity in the infrared, but scheduling was tight, with other high-priority targets queued up for the same window. Gemini's ground-based vantage was limited by weather and the comet's shrinking solar elongation. Coordinating these assets required a level of choreography more common in planetary defense exercises than routine comet work. Observatory directors juggled requests from competing science teams, while data pipelines ran overnight to process and distribute raw frames. Slack threads filled with debates over filter choices and exposure times, as every observation had to count. The sense of urgency was sharpened by the approaching blackout. Once the comet slipped into the sun's glare, Earth-based telescopes would be blind for weeks. The last usable data sets, HST's ultraviolet images, JWST's carbon dioxide spectra, Gemini's color snapshots, would serve as the final record from Earth's perspective. With the handoff to Mars orbiters looming, the ground campaign became a test of global coordination, squeezing every possible measurement from a vanishing target. Mars becomes the solar system's best observatory when Earth's telescopes are blinded by the sun. Orbiters circling the red planet are suddenly tasked with tracking a comet that wasn't part of anyone's original plan. Each spacecraft brings a specialized set of tools, and teams of engineers and scientists scramble to adapt, reprogramming instruments and negotiating precious observation slots. HiRISE, the high-resolution imaging science experiment on NASA's Mars Reconnaissance Orbiter, is known for its ability to resolve objects as small as a desk from orbit. With a 0.3 meter per pixel resolution, HiRISE can, in theory, spot the nucleus of 3I/Atlas, if the background glare and tracking geometry cooperate. But tracking a comet moving at 58 kilometers per second, millions of kilometers away, stretches both hardware and software to their limits. Teams at the University of Arizona and JPL run simulations, tweak exposure times, and fight for imaging windows. The risk is not just missing the comet, but overexposing the camera or damaging pixels if the sun creeps into view. ESA's Mars Express, orbiting since 2003, brings the high-resolution stereo camera, or HRSC. HRSC excels at wide-field, multi-angle imaging, ideal for capturing the full sweep of a comet's coma and tail. Its color filters help separate dust from gas, while stereo pairs may reveal subtle three-dimensional structure in the expanding cloud. The HRSC operations team in Germany coordinates with ground-based astronomers to time exposures for when 3I/Atlas passes closest to Mars's orbital plane. The ExoMars Trace Gas Orbiter, or TGO, carries KC-ESIS, the color and stereo surface imaging system, and NOMAD, a suite of spectrometers built to detect faint atmospheric gases. CASIS, designed for Martian geology, can be retasked to image the comet's coma in multiple color bands. Its rapid imaging allows tracking of changes in brightness and structure during a single flyby. NOMAD is optimized for detecting trace gases like CO2, H2O, and rare organics. By aiming its spectrometers at 3I/Atlas, the team hopes to confirm the elevated CO2 levels, first flagged by JWST, and search for chemical signatures never seen in solar system comets. NASA's MAVEN mission joins with a different perspective: its imaging. Ultraviolet spectrograph tunes into emissions from atomic oxygen and carbon, while plasma instruments measure how the solar wind interacts with the comet's outflow. MAVEN's data could reveal whether the coma's green glow is driven by atomic oxygen or more exotic processes. Its orbit, designed to sample Mars's upper atmosphere, puts it in a prime spot to catch the comet's passage from multiple angles. Mission operations centers in the US and Europe run emergency meetings, weighing the risks of diverting instruments from routine Mars science. Every observation slot is a negotiation among engineers, principal investigators, and project managers. Safety protocols are strict. Cameras must avoid direct sunlight, spectrometers need careful calibration, and dust hazard models must be checked. Sometimes, software patches are uploaded at the last minute to enable new tracking modes or override default safety limits. No single orbiter can capture the full story of 3I/Atlas. Together, this international lineup forms a synthetic observatory, stitching together imaging, spectroscopy, and plasma measurements across orbits and time zones. Ingenuity is found not just in hardware, but in the rapid coordination of teams who, until recently, had never heard of this comet. As Earth's view fades, the responsibility for decoding an interstellar visitor passes to these robotic eyes at Mars. each one poised to gather data that could reshape our understanding of comets and the chemistry of objects from beyond the solar system. Color in a comet's coma is a chemical fingerprint shaped by sunlight and the volatile ices boiling away from its core. In September, 3I/Atlas stunned astronomers as its coma shifted from a muted red to a vivid green, a transformation that signaled something unusual was happening deep within its expanding envelope. The coma's sheer size was hard to fathom, spanning nearly half the diameter of the Sun, over 600,000 kilometers across. This wasn't a photographic illusion or a trick of exposure. The green glow was real, and it demanded an explanation. Traditionally, green comets owe their color to diatomic carbon, CO₂, which fluoresces in the swan bands near 510 nanometers when struck by sunlight. Yet, as spectroscopists pored over data from Gemini, VLT, and JWST, the expected CO₂ emission lines were nowhere to be found. No swan bands, no hint of the classic carbon signature, even as the coma's brightness intensified. Instead, the spectra pointed to a different culprit. JWST's August readings revealed a CO₂ to H2O ratio of about 7.6, an extraordinary value, far higher than in most solar system comets, where water typically dominates. This finding shifted attention to atomic oxygen, specifically the forbidden OI emission at 5,577 angstroms. This green line appears when sunlight and energetic electrons break apart CO₂ and H2O molecules, freeing oxygen atoms that emit green photons as they relax from a metastable state. In the dense, CO₂-rich coma of 3I/Atlas, solar ultraviolet and photoelectrons act as catalysts, turning the region into a factory for green OI emission. Laboratory experiments and previous comet studies support this process, but 3I/Atlas takes it to new extremes. Even at 2 astronomical units from the Sun, the conditions are right for this mechanism to dominate, outshining the dust-scattered continuum and producing the eerie green glow that now defines the comet's appearance. Alternative explanations have been considered. Teams searched for CO plus fluorescence, dust scattering, and rare plasma effects, but the lack of CO and the unchanged dust spectrum made these unlikely. The debate unfolded in real time, with researchers sharing raw spectra and calibration scripts, dissecting every new data release for traces of CO₂ or other carbon chains. Yet, the consensus settled on atomic oxygen as the main driver. The timing was compelling. The green phase began just as the CO₂ output surged, and as the comet crossed the threshold where solar UV could efficiently break up molecules in the expanding coma. Dr. Lina Sato, lead spectroscopist with the JWST team, described the challenge as chasing a moving target with a shifting personality. Each spectrum captured a system in flux, where chemistry and physics collided on a scale rarely seen. The absence of CO₂ wasn't a failure. It was a clue that 3I/Atlas was operating under rules unfamiliar to solar system comets. The green glow became its signature, a marker of interstellar chemistry and ancient ices shaped in another star's nursery. The puzzle remains open. As the coma evolves and Mars orbiters prepare for new observations, the search for definitive spectral lines, CO₂, OI, or something stranger, continues. Each measurement could reveal whether 3I/Atlas is simply a comet pushed to its limits or a messenger carrying secrets from beyond our solar neighborhood. The next question: how does this chemistry shape the comet's structure, and what might the anti-tail reveal about the forces sculpting this alien visitor? A sunward streak slices through the coma of 3I/Atlas, running counter to the classic image of a comet's tail. Instead of trailing away from the Sun, this anti-tail points straight toward it, visible in both Hubble images and ground-based telescopes. The usual explanation, a projection trick when Earth crosses a comet's orbital plane, doesn't fit. The geometry is off, and the anti-tail's persistence over weeks hints at a deeper cause. Plasma physicists and dynamicists have focused on the mechanics. 3I/Atlas is dominated by carbon dioxide, not water, and its outgassing is far from uniform. Sunlight hits the nucleus at a steep angle, driving jets of gas and dust mostly from the sunward side, This uneven activity pushes large dust grains outward, but not evenly in all directions. The strongest jets occur where sunlight is most intense, stretching a snow line farther toward the sun than in typical comets. Grains launched along this axis are bigger and slower, able to survive both radiation pressure and heat for much longer. The result? A real, physical anti-tail, an arc of massive grains that can persist for tens of thousands of kilometers before finally sublimating. Models indicate these grains are at least 10 microns across, heavy enough to resist the solar wind and hold their sunward path. Their survival depends on both size and what they're made of. While carbon dioxide ice vanishes quickly, grains mixed with darker, less volatile material can last long enough to create the observed feature. The anti-tail's brightness drops off exponentially along its axis, matching what's expected when grains are steadily destroyed by sunlight, not just scattered by space. Electromagnetic forces add complexity. As the coma expands, it becomes a testbed for plasma interactions. Charged dust grains interact with the solar wind and the comet's own outflow, creating narrow streams and spikes that can distort the anti-tail. Still, for 3I/Atlas, the main sunward feature is driven by grain survival and anisotropic jets, not exotic plasma effects. The ion tail, shaped by the interplanetary magnetic field, points away from the sun as expected, clearly separated from the anti-tail's path. Some have speculated about non-natural causes, engineered structures, self-organizing plasma, even interstellar technology. But the data don't support these claims. Every feature fits within the boundaries of known cometary physics, though pushed to extremes by the comet's unique chemistry and activity. Dr. Rafael Ortiz, a plasma physicist from the Mars Orbiter campaign, sums it up. If you want proof of the extraordinary, you need to rule out the ordinary first. So far, the anti-tail is a triumph of natural mechanics. The real test is still to come. As 3I/Atlas rounds the sun and Mars orbiters gather data, models of grain size, jet anisotropy, and plasma coupling will face their toughest challenge. If the anti-tail fades or fragments as predicted for carbon dioxide-driven grains, the case for a natural origin grows stronger. If not, new physics may be waiting. After perihelion, 3I/Atlas enters its most unpredictable phase. The models split into camps, each with a different vision for what happens next. Some forecast a slow fade, brightness dropping as volatile ices are spent and the coma shrinks, leaving only a faint remnant to drift outward. Others warn of a final flare, a surge in brightness triggered by fresh pockets of carbon dioxide or a sudden collapse of the nucleus, echoing the fate of comets that have fragmented under solar stress. A third possibility lingers on every dynamicist's scorecard: disintegration. If the nucleus is as porous and fractured as its wild activity suggests, perihelion could spell its breakup, scattering fragments that would briefly spike the light curve before vanishing into the void. Dr. Mara Valenti, a comet dynamicist tracking the event, describes the next weeks as a stress test for every theory about interstellar wanderers. Her group's simulations map out dozens of scenarios, each tied to specific diagnostics. A smooth decline in brightness hints at simple outgassing. Erratic jumps or sudden drops could signal fragmentation. A persistent green coma after perihelion would point to deep stores of carbon dioxide-rich ice, while a rapid color shift back to red or blue might reveal the exhaustion of those volatile layers. The stakes reach beyond the fate of a single comet. 3I/Atlas is a probe from another star system, carrying chemistry and structure forged in a distant nursery. Its behavior tests the limits of comet physics, how deep ices survive interstellar travel, how dust and gas interact with solar wind, and whether our models can predict the life cycles of objects that spend millions of years between stars. Each outcome, fade, flare, or fragment, feeds data back into planetary defense models, refining how we track and interpret new arrivals that might one day pose a real threat. Speculative ideas, from engineered probes to living plasma, remain on the fringe. No evidence so far supports such claims, but the scientific method demands vigilance. Every anomaly must be checked against natural explanations before invoking the extraordinary. The Mars flyby and perihelion window create a rare laboratory, one where model predictions can be scored against real events and where the boundaries between the known and the possible are tested in real time. Key milestones are already circled on calendars. Mars orbiter data releases in early October, perihelion on October 29th and 30th, and the return of Earth-based views in November. The next weeks will decide which models hold up and which must be rewritten. For now, the story of 3I/Atlas is a live experiment, unfolding at interstellar speed, with every new observation a chance to glimpse the physics of worlds beyond our own. Even with the best instruments, some cosmic visitors leave more questions than answers.